Let's get started here. So today we will finish up the graphics section and start the principal component analysis section. All of you should receive notification via Canvas that the week number 5 quiz has, essentially been graded. Everyone received 5 out of 5 points. So all the groups that needed to be formed have been formed. Are there any questions before we get started here? Okay, so there was a question at the end of the class that I posed regarding these parallel coordinates plots. And that was, you might have situations where you have some overlapping of the lines. And this is not a good example of it, but you can imagine a situation where you have many more observations, and each of these lines that you see in these plots is actually drawn one at a time. And so because of that, you might have some overlapping and you might miss where some of the observations are. And so how can we get around this? And one thing that I said last time was one could change the ordering of the lines being drawn. That would be one way to do it. And so what I've done since our last class is I've added some code to my corresponding program that shows two different ways to change the ordering. So previously, when we used parcord, we said I want to plot information that's in my serial data frame. Variable 1 is the ID number. 8 through 10 is sugar, fat, and sodium. So the way that R is going to work here is that basically observation 1 is plotted first. All the lines for it. Then observation 2 will be plotted next. Well, one thing that you could do is change the ordering of the rows. So now observation 40 is actually plotted first. Then 39 is plotted. So just to show you that indeed that we have changed the ordering here, let me just highlight that segment of code. And you can see how ID 40 is first, ID 39 is second, and so on. So what you could do in a simple case is just simply plot the data this way instead, just to make sure everything looks the same. And since we only have 40 observations, trust me, it does. You can verify that on your own. Now, in situations where you have many more observations, you still might want to look at other viewpoints of the plot. And so one thing that you could do is how about randomly choose which observation is plotted first, which is plotted second, and so on. One way to do that is to use the sample function. So if I say sample x equal 1 to 40, now what I have here is different possible ordering that are chosen at random that I can for 1 to 40. And then I can use that now as my order for the rows in serial and do the plot like that. Okay, so let's move on. So we've been looking at ways of how we can get essentially as many variables as possible in a plot because we have multivariate data. We have one more kind of plot that can be helpful in this situation. These plots are called trellis plots. Every once in a while you hear people call them coplots, where the co stands for conditional. And that name comes about is that we try to look at relationships between variables by conditioning on the values of some of our variables. So a very simple demonstration of this is as follows. Let's say that I have variables x1, x2, and x3. And let's say x3 is a categorical variable. And maybe it has categories 1 to 6. Okay? Well, so I have 3 variables. I like to be able to look at all these variables in a scatter plot format. And so let's say I did a plot of x1 and then x2. Here's a scattering of my points. What do I do about x3? Well, you could have the plotting point correspond to the color, you could have changed the color of the plotting point corresponding to x3. You could change the shape and so on. We've seen that. But in this simple setting, let's say we do something different. How about we plot this so that x3 is equal to 1? So only for those observations that have x3 equal to 1, let's do a scatter plot of x1 and x2. So notice I'm conditioning on its value. Well, you might be wondering, well, what happens if x3 is equal to 2? Well, I could do another one of these plots as well, where I have x1 versus x2, and so on. And I could keep on doing these plots. Now I'm running out of space, but I think you get the point. Let's say that x3 is equal to 4 here, x3 is equal to 6 there, and so on. So I'm conditioning on particular values. This is what's called a trellis plot or a coplot. And you can kind of think about, or you can kind of see why this is kind of, why it is called a trellis plot, is this shape of how I'm organizing all the plots. It kind of reminds you of a actual trellis that you might see like in a garden situation, where I have these squares or rectangles representing these relationships that I'm looking at, conditional on some of the variables. Now, in terms of the terminology here, each of these rectangles, each of these squares is called a panel. That's going to be important as we go along here. Now, you might be wondering, well, what if x3 was not a categorical variable? How could I do this? Well, let's say x3 now instead ranged from, let's say 0 to 6 on a continuous scale. So what I could do here is let's let this first panel be x3 equals 0 to 1, the next panel 1 to 2, and so on. Another way that I could approach this also is to allow some kind of overlapping amongst these, amongst x3. So maybe x3 is equal to 0 to 1.1 for the first panel, and then for the second panel, x3 is equal to 0.9 to 2 or something like that, to allow some kind of overlapping. Okay, so that's that's basic explanation of these trellis plots. Now, very often, whenever trellis plots are presented in the class, a particular example is always shown because it helps demonstrate the importance of this, and it actually involves a data set where people had used it for many, many, many years to teach stuff, and no one had noticed a certain characteristic about the data set until it was until these trellis plots were applied. And so this is the actual plot itself, and unfortunately I cannot get all of it on one screen. Okay, so what we have here on the x-axis is barley yield. On the y-axis, we have about, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 different varieties of barley. Inside each panel, I have the barley yield for a particular location in Minnesota, and I have 2 different years of yield. So let's see, so the blue is 1932. So you can see this is an old data set. And the magenta is 1931. And so we can see here for Grand Rapids that 1931 had a higher yield than 1932. And it was consistent across the different varieties. And if we look at throughout all of these different locations in Minnesota, we see the same pattern where 1931 is greater than 1932, except for one location, Morris, which is in northwest Minnesota. Otherwise, generally speaking, 31 is greater than 32. People had not noticed that until this plot was actually used. This data was a standard data set that was used to demonstrate analysis of variance methods in multiple books, and no one had noticed that before until this plot was used. Now, and so you might be wondering, well, that's kind of strange. These are all Minnesota farming locations. And while Minnesota is a large state, why would this occur at only one location? And so when this actually first was discovered, actually in the 1990s, people were wondering, wait a second here. Maybe it was a data entry error. Maybe somebody simply changed the years. And interestingly, for about 20 or so years, then from the early 1990s to 2013, people thought, yeah, it must be a data entry error. But in a paper in American Statistician in 2013, they actually did find, through additional investigations, that simply was an unusual occurrence. That for some reason, I forget what the reason was. Maybe you could think of maybe they had a little bit different weather situations there in Morris that year. And so anyway, so kind of a interesting story. Now, to do these plots in R, there is a coplot function in the graphics package that will do them. I have found, though, that this to not be as good as functions that are available in other packages. So while my standard of teaching R in this class or any class is to always try to use what's in the default installation of R, but the exception is if something's better, then yeah, I'm more than happy to use some other package. And also if I know that the package is well established, it's been around for a while, it's not going to go away. That's often a problem with R, is that you have all these people that are contributing new packages, and then after maybe about 5 years, they just say, well, I'm not going to maintain that package anymore, and it gets archived. And it may or may not work in the future. So there's 2 packages out there that produce these plots that I would recommend. This package is the one that we're going to look at, the lattice package. I find this one to be, it will be easier to present with respect to teaching. The syntax, the coding is going to be more familiar to us than what ggplot2 does. And so that's why I think that's a better choice in this class. Now, you will not be an expert in how to use lattice or lattice after this class here today. But what I'm going to do is show you some particular plots that you can think of as templates on your own. And then if you choose to go beyond those templates, let's say for your project, go ahead. Explore this package some more, see what you can do with it. Okay. So we're going to go back to the serial data set. And what we're going to do, I guess, immediately next is some data formatting. And this is good to learn in any situation where you need to use R, because very often you need to format the data a different way than what maybe is given to you by default in order to get functions to work. And so one of the most common things that people have to do is to go from what's called a wide format of data to a long format, or go back in the other direction. Okay, so to help explain that, what I've done is just constructed a simple data set. So this is not the serial data, but just a simple data set where this kind of thing can happen. And so this is what the data set looks like. It's in a data frame. I have an ID for each row. So maybe what we have here, at least when I was constructing this data set, I was thinking of maybe you can imagine, let's say, a clinical trial where a pharmaceutical company is trying to investigate, does a new drug work? Or how about we phrase it this way? Does a new drug lead to side effects? This would be what's often referred to as a phase 1 clinical trial. And so in these particular situations, they will give the drug to multiple people, and they will observe over time, does the person have a particular side effect or not? And so let's say we have person 1 or subject 1. They like to use subjects in this particular in phase 1 clinical trials. I also have an ID number associated with each of them. Well, I guess I have two unique ways to identify them. They probably weren't both needed, but I just ended up organizing it this way. We have the age of the person. And then let's say 1 hour after the drug was administered, we look to see, does that person have a particular side effect? Maybe they have blurry vision, or maybe they're dizzy or something like that. Maybe they have a headache. And a 1 means yes, 0 means no. Then at time 2, maybe 2 hours into the study, we look to see again, do they have some kind of side effect? In this case, this person does not. So what I would like to do next is with this data, and we just have simply 3 observations to make this simple, is I like to reorganize it. Organize it in a manner where I'm going to take this time 2 and put it right below time 1, but then also include the corresponding labels as needed. Also reproduce, let's say, their age. So the current format here is what's called a wide format. Notice what I'm observing, my response variable is presented kind of, if I had time 3, time 4, time 5, it keeps on getting wider. But what I want to turn it into is the long format, where now for each additional time, each additional response for the time, now the data frame is going to get longer. And so to do that, the simplest way is to use a function called reshape. Makes sense? I am reshaping the data. This is in the base package of R. And so to use this particular function, I specify, well, what's my data that I want to reshape? Then I need to say, well, how I'm going to identify each row of the original data set uniquely. And so that's where I put my id.name variable. Then I need to say, okay, well, what are my response variables that I have here that I essentially want to stack one on top of the other? Well, that's where varying comes in. You can think of it as the observations are varying through time. That's where the name essentially comes from. And so here I specified time 1 and time 2. Well, now I need to also have a new name for this column that contains all my responses. And so that's where v names, variant names, comes about for the argument name. And how about we just simply call it response? And then I need to say, okay, well, I'm going from a wide format to a long format. So I want my new format to be the long format. So I say direction equal long. If there were some variables that I no longer need, like id.number, remember that was kind of duplicate. How about we just throw that away? So I say drop id.number. And then lastly here, and this unfortunately was, it's in my code, my program, but I, for some reason, left it out of the notes here. Time var equal time. What that corresponds to is I need some way to identify, am I talking about time 1 or am I talking about time 2? So the general argument name just happens to be time var because very often we're observing information over time. If you've heard of the concept of a longitudinal data set, this is essentially a longitudinal data set. And so time var equal time. What that means then is this is going to be the name for whatever I'm going to put there for, okay, this was my first variable that was in varying. This is my second variable in varying, 1 and 2. That's the default of how R will identify them. And so if I put this all into set 2, we can see that now I have this long format. Notice how age is duplicating for subject 1. I have all the corresponding response values that were originally in time 1 and time 2. So there's a lot of arguments for this particular function. And the way that I usually approach this whenever I have to do it is I find an old program where I've done this before. I copy and paste that code into my new program where I need to do it. And then I just change the various argument values. That's the simplest way to do it. Now, if you notice here, there was some extra stuff that was given. We don't need that. So a quick way to take care of it is to say row.name set 2 gets null, meaning just throw it out. I don't need any row names. This is one of the few times where in R you can make an assignment where on the left side you actually have a function name. One of the very few times. So you might be thinking, okay, well, great. Now I have this long format. Could I go back to my wide format? Yeah, we could. So I could say reshape again. My data is in set 2, the long format of the data. Now I need to say, okay, what variable helps me to differentiate between, let's say, time 1 and time 2? Remember that variable was called time. So I say time var equal time. What variable uniquely identifies, let's say, each, in this case, person in my data set? Well, that was the id.name. And if I say direction equal wide, now it's going to go to a wide format. And you can see this is what R did. It puts it in essentially the same format that we had before. It gives some extra information that we didn't need, though. Okay. So that then is how you go from a wide to a long and long back to a wide. Now let's apply this to the serial data set. So with the serial data set, what I'm going to need to do is I need to, in order to get this, to do this trellis plot coming up, I need to restructure the data so I have all the sugar values, and then I have all the corresponding fat values right underneath it, and then, unfortunately you can't see here, then all the sodium values right underneath that. So similar to what we had time 1 and time 2 before, now we have sugar, fat, and sodium. I just need to reorganize it so that it goes into a long format. Each of these serials is uniquely identified by the serial variable. So to do this, I can do this as follows. Reshape data equals serial. My ID variable is ID. Let me come back over here. This is just a duplicate. I could have used serial as my ID variable, but remember in the data frame I also have ID itself, 1 to 40. So that's what I chose there. I'm going to remove a bunch of the information that I don't need anymore. What is varying? Well, it's the sugar, fat, and sodium. That's what I want to stack on top of each other. Then, rather than using the default name for the variable, I come back up here. Sorry. Rather than using the default name that R is going to sign that differentiate, is this corresponding to, in this case, time 1 and time 2, and R calls this variable time. Well, I guess I had time var there. Instead, what I'm going to do is call that content. Is it sugar content? Is it fat content? Is it sodium content? So I decided to use the name content. Something I could use again, even a different name. Then what am I going to call then this new variable that I'm creating that has the actual sugar, fat, and sodium values in it. I'm going to call it amount. In terms of what's the time var itself, instead of allowing R to call it, this is for that first variable, this is for the second variable, this is for the third variable for what was in varying, I'm going to say times, this is a new argument we haven't seen, let's call them sugar, fat, and sodium. That makes sense. And direction equal long. And if we go ahead and run this segment of code, we can see that the first 6 observations are only the sugar ones. The last 6 observations are only the sodium ones. I guess we can look at the whole thing just to prove to you indeed that we now have, instead of 40 rows, we have 120 rows. And everything's nicely organized: sugar, fat, and sodium. Okay? We can do exactly the same thing with the standardized data as well. And so I'm just going to go ahead and do that. I'm going to put this into a data frame called z.serial.long. Okay. So the first thing that we're going to do is some histograms. We're going to work with the standardized data here because that will allow me, if I wanted to make comparisons between the sugar, the fat, and sodium, because it's all on the same scale now. And so let's take a look at the plot first, and then I'll explain how we can use the lattice package to actually create the plot. So we're doing histograms for each of the different types of nutritional measurements that we're doing: fat, sodium, and sugar. And we're doing it by shelf. So for example here, let's actually look at this one. So the sugar standardized value is what's represented on the x-axis. The y-axis, as you would expect from a histogram, you could have count. Here, R does by default percentage, like what percentage of the observations were within one of the categories in that histogram. And this corresponds to shelf 2. Now, how do I know that? Well, it's because of this little line here. So since shelf is a numerical value, and I guess R doesn't check, well, is there just a finite number of numerical values? I mean, is it more of a, let's say, just integer values versus a completely continuous? What R would do is, by default, just use then these lines here to indicate, okay, since this is far left, this means this lowest shelf number. This is far right, this is the highest shelf number. That's how it does it. We'll look at how we can actually get the shelf number on the plot shortly. So this is for shelf 2. And we can see that the sugar content for shelf 2 seems to be all greater than 0 in terms of the standardized values. And that corresponds again to what we saw before. It seems like there's higher sugar content cereals on shelf 2. Nothing new there. Now, what's interesting is that we haven't really looked at a plot yet to see this. Look at shelf 1, sodium. We see somewhat of a similar pattern there. Higher sodium content cereals tend to be on shelf 1 for this sample. I don't have a good reason why that might occur. I do know that there tends to be like cornflakes on shelf 1. So how did I do this plot now? Actually, I can do this in Word. Oops. So the lattice package is not in the default installation of R. Well, let me actually double check that. I'm sorry, it is in the default installation of R. But the key is it's not always made available to you to use when you start R. So you still need to say library lattice. The same thing with the mass package as well that we use for parallel coordinates plots. And so to do these trellis plots for histogram, we simply say histogram, parentheses. And this is like a formula argument that we've seen before, like for example with the LM function. Instead, it just calls it x. X equal, and this is where I say what I want to plot, tilde amount. Notice how when we've had formula arguments before, like with the LM function, we do something like this. Y tilde x, where the x represents my independent variable, explanatory variable, my y represents my response variable. Here, a histogram, of course, just you're plotting essentially one variable, and you're plotting on the x-axis typically, the way that histograms are normally constructed. And so that's why we only need to put amount there. So this is the actual sugar, fat, or sodium content. Then we have a vertical line here. This essentially means the word given. So in your very first stat course, you talked about conditional probabilities, such as the probability A given B. So given that B occurs, what's the probability of A? With trellis plots, we are conditioning on particular values of a variable. And so that's why this same syntax is being used here. So I have amount given the content variable, meaning is it sugar, is it fat, is it sodium, plus, you can think of this as and the shelf variable, which tells me again which shelf we're on. My data is in z.serial.long. Then I have some other arguments that is what you would essentially expect in terms of like the title of the plot. One very, very, very odd thing is this. Layout. 3, 4. That says, well, how do you want to structure the panels? Now, you might be thinking, okay, that means 3 rows, 4 columns. That would make sense because whenever we do matrices, we always say the row number first. Instead, this is the number of columns, and this is the number of rows. And we can see in this plot, we have 4 rows, 3 columns. Kind of odd, but that's the way it's done. Okay, any questions? Well, how can I get the shelf number on the plot? There's a few different ways. One way that I'm going to focus on here is that I'm going to change how R recognizes the shelf number. Rather than R saying, okay, I have this numerical value that happens to have values of 1, 2, 3, and 4. I don't necessarily know if these are only going to be integer values or whatever. I'm going to tell R, hey, treat this variable as a categorical variable instead. The way to transform a variable to be categorical in nature is to use the factor function in R. So if I come back over here to R, notice if I say factor and I pull shelf out of my standardized data frame, look what happens. Now R recognizes, oh, there's only 4 different levels, and I'm going to treat this as a categorical variable. And so what I'm going to do is create a new data frame called z.serial.long2, where I take my original data frame, and then I'm going to add a variable to it called shelf.char for character. I could call it categorical or something like that. I just chose this name. And it's going to be the results from that using the factor function. And so now when I use this new variable in my histogram function, now we can see the 1, 2, 3, and 4 there rather than seeing the darker lines to represent the numerical value. Still, you might be wondering, well, could we just simply say, well, this is shelf equal that? And yeah, you could do that. And so this is some more helpful hints about how to best use R. And so what we can do is combine the word shelf, combine the the phrase shelf equal with those actual shelf numbers. And the way to do that in R is to use the function called paste, meaning I'm going to paste together the word shelf equal with all the shelf numbers. So look, I'm going to highlight that segment of code and run it. And there you can see how everything's nicely pasted together. Is that big enough? Can everyone see that fine? Okay. So I can then also turn this into a factor or a categorical variable using the factor function again. And now when I run that segment of code, I get shelf equal. And so that's a better version of this plot. Now, there are ways to control how R constructs the contents of what's in each panel in terms of what's actually being plotted. And the way to do that is to add an argument called panel. What do I want actually plotted inside there? And so this is where I can show you a couple examples. But, if you really are interested, there's many other different ways to work with this. And so I'm just going to show you a couple examples. And the way that people usually use the panel argument is to write a function right inside this function call, where I'm going to write a function. So we've seen just a little bit about writing your own functions before. And I say function X. That's going to correspond to what's there. So R will automatically pass into this function this information. Then a ... This is R's way of saying, okay, at times there might be other stuff that I want to actually pass into the function, like anything that I have here, if that function calls for it. And so I'm going to allow that to happen. And so that's what the ... represents. And you can see inside this function, so I use the curly brackets to indicate the beginning and the end of the function. And you can see from the names here, I'm going to apply a function called panel.histogram. And so what that's going to do is simply draw the histogram like what we've seen before. And then I'm going to also draw what's called a density plot. And we've talked about this before, where in your very first stat class, you talked about doing histograms like this. And to approximate the shape of the histogram, what would you do? You draw a line that kind of goes through the middle of those tops of those bars, that histogram. Well, by doing what's called a density plot, that's kind of a fancy way to do this. I think we saw this actually with the scatter plot matrix function. And so I'm going to do that. I'm going to make sure that the line that I'm going to draw there is black, just to show you what you can do. And here's the corresponding plot. So now you can see the shape of everything there. Okay. So there's other kinds of trellis plots in terms of, rather than working with histograms, we could do scatter plots. That's what I started off at the very beginning talking about. And so I can use a function called XY plot. That seems like a good name for a scatter plot function. XY plot. And then let's say on my Y-axis of each of my panels, I want sugar. On the X-axis, I want fat. How about I condition on the shelf number? And this is what we get for the plot. And so what we can see here once again is that for shelf 2, notice how the cereals have higher sugar content in comparison to the others. So one thing I should have mentioned before that I didn't is that, by laying out your plots like this, this allows you to compare across the rows of each column. And we can see how shelf 2 is quite different from shelf 1, 3, and 4 by arranging everything in that way. And so you could also compare across the rows as well. And so we can see like how shelf 1 does have some lower sugar ones compared to shelf 2. We can make this even fancier. We can come back to this using this panel argument again. And basically what I did here, I went through the help for the lattice package to figure out how could I draw a regression line on the plot? How could I add grid lines? And how could I just simply do the regular old scatter plot again? And so here I actually estimate a regression model to each of those panels separately. One could also do three-dimensional plots as well. I could use the cloud function for that purpose. And so I have a three-dimensional scatter plot here. And, unfortunately, it doesn't allow you, like the RGL package, it doesn't allow you to click in there and rotate the plots. I think it'd be really cool if I could, click, in this plot here, and then automatically rotate all the plots in exactly the same direction. Well, maybe you should write your own package and upload that to CRAN, and I think everyone would be really happy with that. Let's get back to the case where now I have, let's say, a variable that I want to condition on, but it's not categorical in nature. It's actually more of like a continuous variable. How can I include that now in my plot? And what I introduced at the very beginning, talking about these kinds of plots, is that you could, let's say, for a particular range of, let's say, x3, do a plot. For another particular range of x3, do another plot. When you do that, that's called forming a shingle. So how do I form shingles? Well, let's say I want to do a plot of fat versus sodium. I want to do a plot of sugar versus fat. And my third variable is going to be sodium, where I'm doing a scatter plot. I should have said that. Scatter plot of sugar versus fat. And each panel is going to correspond to values of sodium. And so to get R to automatically form this, basically categorizing this essentially continuous variable, I can use a function called equal.count, where the x argument, sodium, how many different shingles do I want to form? How many different categorizations? That's not very concise. How many categorizations do I want to have? How about 3, just to demonstrate this? How much do I want to overlap each of those categories by? How about 10%? So what that means is that for that first shingle, it's going to share about 10% of its observations with the second shingle. And so when I create this sodium dot group object, we can see what we have here. We have my original data. I have these intervals of sodium. So notice the very first grouping goes up to 5.00. The second grouping starts at a little bit less than 5.00. I have 14 observations in that first group, 14 in the second, 15 in the third. If you add those up, you get 43. Remember, we only have 40 observations. So that number is higher because I'm allowing that overlap, that 10% overlap. Okay. So if I use the XY plot function again, sugar y-axis, fat x-axis, given that sodium group. And just to make things a little bit more interesting, how about we also allow the shelf number to be corresponding to the color of the plotting point itself. So I can use an argument called groups that allows me to change the plotting point color. auto.key equal true. What that just basically means, R, you go get the legend, you put it on there, that's fine. And so this is what we have. So again, sugar on the y-axis, fat on the x-axis. And notice we have this darkened colors for each of, let's say, the panel labels. R will not plot what the actual numerical values are for sodium, but rather it gives kind of a visual description that, yeah, we can kind of see I have a little bit of an overlap. I have a little bit of an overlap there corresponding to the sodium values. This black square that's in the middle represents that this is the middle category. Okay, any questions? Okay, so let's talk about, briefly, an example where I've actually put this type of plot into practice for an actual paper. So again, this was from a statistical research paper. And what I wanted to do was compare 8 different statistical methods via Monte Carlo simulation to see which method worked the best for a hypothesis test that I wanted to perform. So what I did was I used a type 1 error rate of 0.05. I simulated data so that the null hypothesis was true. Now, depending upon your background, at least those of you who would have Stat 801 from me, I would talk about how to do these Monte Carlo simulation studies or investigations in a simple sense. And this is exactly what I would, it's exactly the same. But let me back up here in case you've never seen something like this before. So if I say alpha is 0.05, that's the probability I reject HO given that HO is true. That's what a type 1 error represents. That's what the alpha level represents. And so what that means then is if I were to, let's say, somehow simulate data 500 times, where I simulate in a way where I know the null hypothesis is true, then I would expect to incorrectly reject HO 5% of the time or 25 times. That's what alpha means. And so in a research setting, we often do studies like this where we want to compare various hypothesis testing methods to make sure that indeed I'm only rejecting 5% of the time incorrectly. Some people refer to this as, does the hypothesis test hold the correct size? And so in this particular case, I simulated 500 data sets. Now, again, I would expect 25 of the times out of 500 to reject HO incorrectly. Now, it doesn't mean that I'm going to get 20, even if the method's working, even if the hypothesis testing method works correctly, doesn't mean I'm going to get exactly 25. There's going to be variability from one set of 500, let's say, trials to another 500 trials. And so I might get 23 or I might get 27, where I'm not going to be worried that the statistical method is working poorly. And so what one could do is use a normal approximation to a binomial to form what kind of looks like a confidence interval for proportion that you would see like in Stat 801. It's very closely related, but not exactly right, or not exactly. And so the main thing that you need to get out of this is that if my method is working correctly, meaning it's rejecting 5% of the time, I will be okay to be between about 0.03 and 0.07 as the actual observed percentage of times that the method is actually rejecting the null hypothesis incorrectly. If I'm outside that range, then I'm like, uh-oh, this hypothesis testing method is not working as advertised. Maybe I shouldn't use it. And so this is what I did here. So for 500 simulated data sets, I calculated for about 8 different methods. The first one's called RS. The last one's called bond. And I looked at, well, how often, what's the proportion of time that I reject? In this case, for this method called RS, it doesn't even matter what RS represents. I got 0.052, so very close to 0.05. This Bonferroni, 0.038, or Bon. It is actually Bonferroni. This is still within that range, so I'm okay with that. But also, when I simulated data, I controlled something called an odds ratio. I let them all be equal to 2. I controlled my sample size. I let it be 20. I was working with contingency tables here, so I could actually control probabilities in the contingency tables. And so I set them to be 0.6 and 0.8. And then also the size of my contingency table to be 2 by 2, 2 rows, 2 columns. And then I said, okay, well, how about we change the odds ratios? And I did this a whole bunch of different times where I'm changing the table size, the marginals, the sample size, the odds ratio. So I'm forming a multivariate data set. And rather than my paper to display everything in this very, very long table like this, it would make it difficult to make sense of everything that's actually being displayed, I did a trellis plot. And this is what it looks like. So this is actually summarizing, I think, 496 different numerical values that would have been in that table in terms of what is actually right here. And so let's zoom in. Let's see here. All the way over. So we'll look at this particular panel. So you can see the 8 different methods that I'm using to perform these hypothesis tests 500 times. The green lines are drawn at 0.03 and 0.07. And if I page down here, you can see the numerical scale. This is the proportion of times that I'm actually rejecting. So basically this scale goes from 0 to 0.2. So this would be 0. This would be 0.2. Okay. So anything that's between those green vertical lines, which is drawn at 0.03 and 0.07, means the method worked. Anything outside means you have problems. And so we can see with this RS and this quasi method, it's rejecting too much. You wouldn't want to use those hypothesis testing methods then. For this M-logit method, you don't even see any plotting points. That's because it's rejecting more than 0.2. So you really want to stay away from that. And I should also point out I'm using 2 different sample sizes there, 100 and 200. And so as I page down here, keep your eyes on the same column. Look what happens as those odds ratios increase, that OR. Do you see a trend? Yeah. Some of these methods are now rejecting more often. Okay? And so that's what then I talked about in my paper, that, okay, some of these methods don't work. And the amount that they don't work gets even more as these things called odds ratios increase. And this is easily seen from doing a trellis plot here, rather than having to look at like 496 different numbers in a table. Okay, any questions? Now, you can see with this is a quite complicated plot. And so here's a little bit of a helpful hint whenever you have a very complicated plot, whether it's trellis or some other type of plot. What you actually see here are actually, let's say, 2, 3, 4 different, let's say, plotting windows that I created in R. This was one. This was another one. This was another one. And this was another one. And what I did was I copied and pasted those plots into PowerPoint. in a slide. In that slide, I actually added manually these labels at the very top of the plot. I also removed some of these y-axis labels that were in some of the other panels because they weren't needed. And so my point is to talk about this is that when you have a very complicated plot like this, do as much as you can like in R, then you can move it over to PowerPoint or some other graphics or some other software package, and you can add content to it much more easily there. So just a little bit of a helpful hint. Okay, so that concludes in the graphics section. So for the remaining part of our class, we're going to talk about our next set of notes for principal component analysis. So as I think I've mentioned in this class before, the day before that we have class, I always essentially step through what I plan on talking about in class. And what that basically means is that, okay, I can usually cover about 20 or so pages of my notes, just from my experience, I know that. And so I might look over 25 to 30 pages of my notes. And I actually go through what I'm going to say in class. I go through it in my head just to make sure everything, I think everything's going to work fine in class. It gives me a chance to also double check some of the stuff that I have in the notes, and also check to see, do I like how I'm going to present this in terms of like ordering and stuff like this. And every once in a while, when I'm doing this, and this usually takes at least an hour, maybe 2 hours, I find, I don't like how I'm going to present, how I was planning on presenting that. I want to make some changes. And so, at times you'll see, maybe I'll put like in a red font where I have maybe additional wording in my notes. I say, hey, this is something I added after I posted the notes. In this particular case yesterday, when I went through this, it's like, I would like to actually reorder a lot of the stuff that's in my notes. And so yesterday I ended up spending about 4 hours reordering the stuff that's in the notes. Now, unfortunately, too, I didn't get done with reordering the stuff until about 12:30 last night. Because it took a while, and I didn't always have a whole block of time to do everything all at once. So in my notes, or on my webpage here, what you've probably originally downloaded maybe to your computer already is this document called pca.docx. What I uploaded to my course website last night about 12:30 is pca-new. Now, both sets of notes have essentially the same material. The thing is, it's reordered. And I chose to do that because I thought, I think it will be easier for students to understand it if I reorder some stuff. So, if you have access to your computer now, I recommend, and you're following along, I recommend that you download the pca-new file now, and we're going to go through that file. Also note that I just simply changed the ordering of some stuff in my Goblet PCA.R program to be Goblet PCA new.r. Okay? Now, interestingly, when I was going through my course notes over the summer when I was updating everything, I thought, I think if I did reorder this would be helpful. And then I don't remember why, but I concluded, no, let's just go with the same order that I had used the last time that I taught this with, very small updates. But then when I actually sat down yesterday and was going through the notes, I thought, no, let's do this reordering. So sorry to make this last minute change, but please download these new notes. Okay, so what is principal component analysis, or PCA for short? Well, what we're trying to do in this class is trying to make sense of having many variables in our data set. Understand trends. Understand maybe there might be some outliers. Understand our data, but we have lots of variables, and since you have lots of variables, it can be difficult to make sense of it. Now, whenever you have, let's say, multiple variables, you understand that some variables might be closely related to other variables, while some variables are not closely related to some variables. What I mean by related, let's say correlated. And so to try to make sense of having a lot of variables, what principal component analysis does, it takes a set of correlated variables and transforms them into a new set of uncorrelated variables with the hope that these new variables that you're forming can essentially take the place of your original variables. And also, you need less of these new variables than what you had with the original variables. So let's say if I had originally, let's say 10 variables, we'll call these the old variables. Think about how you would view that in a plot. Well, you probably have to use like a parallel coordinates plot or a stars plot, and those aren't going to be perfect in understanding all the relationships. But if you could somehow transform these variables to, let's say, 3 new variables that represent distinct aspects of your data. In other words, they're going to be uncorrelated. Then think about how you could use now plots to represent these 3 new variables. You could easily do a scatter plot. And so then it would be advantageous to use these new variables rather than old variables, as long as you're not losing out information that were present in the original 10 variables. So these new variables are actually called principal components, or PCs. So this is what a new variable, a PC, could look like relative to the serial data. So this new variable, let's just call it Y for the lack of a better name. And all I'm going to do is find a linear combination of the sugar variable, the fat variable, and the sodium variable. Where, just because I just decided to write it out like this, where it just so happens that the sugar variable and the fat variable have negative coefficients, numerical coefficients. The sodium variable's a positive coefficient. And so often you're going to be left within the case of, well, what does this new variable represent? And, simply put, in this particular case, you can think of it as a difference of the sugar and fat versus sodium. Okay? This is what we're going to be doing. We want to find out what number should I put there. So then the objectives of principal component analysis is as follows. First, discover the true dimension of the data. What that means is if I have 10 variables, maybe instead I only need 3 variables to really understand it. Where have we seen that before? I'm going to go back to the data distributions and correlations section. There we go. So if you remember, we looked at a plot like this. We had a bivariate normal distribution, and the covariance matrix was such that in the end, when I did a contour plot here, it was very, very narrow. And what I said at that time is that, well, we do have variability in this direction. We have variability in this direction for x1 and x2. But perhaps we could find a new coordinate system where I rotate things, as represented by the green here, where now we can see we have variability in this direction, but I have very little variability here. And in the end, if I could use this new coordinate system, I only need to know one of these, let's say, new variables to really understand in this case, my multivariate normal. And so the true dimension then here is 1 versus 2. This is exactly what principal component analysis is going to do. These new principal components that you're finding is essentially going to do that rotation there, if you want to think of it in a graphical sense, to help you understand your data. Oops. So when I say true dimension, Dimension corresponds to the number of variables that we really need. So originally we might have, in our general sense, we've always said that we have P variables of interest. Maybe we only need D new variables. That's my dimension, true dimension. And then what we want to do, and I've kind of discussed this already, we want to try to interpret the variables. So in other words, interpret what we see here. This can be very difficult. Sometimes, yeah, that makes sense. Other times, like, well, I don't know why it's that. So we would like to be able to interpret if possible. Principal component analysis is used in a number of different situations. It's usually used with some other. It's usually used as, let's say, at the very beginning of analysis to get a better understanding of your data before you use a more sophisticated method. So, for example, you could use it for data screening, like to find that maybe you have some outliers. Now, obviously, if I had a scatter plot like this, well, I know this is an outlier. But what we've seen, like with a parallel coordinates plot, you can identify outliers that way too. The key, though, is it still can be difficult if the reason why a particular observation is an outlier is not just because of one variable, maybe it's because of 5 different variables. And so if I'm able to, let's say, reduce the dimension of my data so that I have less new variables than I had for the original old variables, perhaps then this principal component analysis will allow me to figure out where I have outliers. We'll see examples of with an actual data coming up. It can be used also to help. I'm going to use this word, I don't mean it in a formal sense, to validate what's done with something called cluster analysis. So in cluster analysis, and we'll have a whole section of this coming up, cluster analysis is used to basically put observations into groupings where the observations are similar to one another. And beforehand, you don't know what any kind of groupings were. You don't even know how many groupings there might be. And so to help, and let's say again, if you have 10, 20, 30 variables, it can be difficult to judge, well, is this cluster analysis doing what's doing? Is it making sense? Is it really putting together like observations? Well, if you could reduce your dimension from, let's say, 10 to down to 2 or 3, well, then you can look at it visually. Do these clusters for these observations, these like observations, make sense? It can be useful when you want to predict classifications. So, for example, with the place kicking data set that we've seen earlier, where I have either a place kick as a success or it's a failure. I know in my data set, if an observation is a success or a failure. I might want to be able to somehow come up with a model to predict that. And if I have, let's say, lots of other variables, let's say independent variables that are used to predict these two classifications, it may be difficult to figure out, are these predictions making sense or not? So what I could do is take these original variables, let's say, apply a principal component analysis to it so I have a smaller new set of variables, and then look visually, do the results make sense? So we will get to do this with principal component analysis. We will get to do this with principal component analysis. What we will not do with principal component analysis is this, because this will be taught more in a regression course, like a Stat 870. And just real briefly, if you've had a formal regression course, there are times where you might have what's called multicollinearity, which basically means is that you have variables that are highly related to one another, meaning highly correlated. One way to get around that some people use, and I'll just say it causes problems in your analysis set. One way to get around this is to replace your original variables with these new principal components. Okay, so this actually might be a good place to stop because now we're going to get into the mathematics behind all this. So that gives you some motivation. So what's next in our class? Then I'll have my usual office hours. On Tuesday, we will continue with principal component analysis. It's going to take us a few classes to get through all of it. We're going to have two main examples. Of course, the serial data, just a good one to always go back to, but we'll also start doing the goblet data. So if you haven't looked at the practice problems for the graphics section, please look at that before our next class, because there is some work with the goblet data in that set of practice problems. Then looking further ahead, project number 1 is going to be due on Friday, October 6th. Next week, I will also spend some time talking about the principal component analysis part of project number 1. By the end of next week, I strongly recommend that you send me your data, send me the first part of the project there. Give me a draft of that explains your data so that I can approve it, or I can say, hey, maybe you need to look at the data this way, or maybe, sorry, you're going to use a whole another data set. I doubt that will happen, but it is a possibility. So the sooner you can get that data to me, the better. And then, of course, then our next test will be mid-October. Are there any last questions before we end here? Okay, that's it for today. Just send me one.